and my name is Dong Shin, and I'm from LIS EPFL, advised by Professor Floriano, and also Professor Auke Ispert is also helping me on this project. So I'm going to talk about development and application of a series parallel elastic actuation. So I'm going to start with the big picture for my NCCR project, since this is my first presentation in this NCCR group. And for disaster situations like the picture, it's hard to overcome the shown obstacles with terrestrial locomotion. So to detour the obstacles, aerial vehicles are favored. And for quick response in a disaster situation, a fixed-wing vehicle is preferred. But there are some obstacles which cannot be cleared with fixed-wing vehicles, such as this kind of obstacles where there's a really sharp curve, or it's a really narrow tunnel, or if there's and also a narrow pathway where the wing cannot be spread out. So for these kind of obstacles, terrestrial locomotion will be preferred. So we want to develop a multimodal platform capable of aerial and terrestrial locomotion. And we want to equip a fixed-wing vehicle, a pair of legs, and at minimum, the legs needs to have the speed, maneuverability, and autonomous takeoff, because the speed is required for fast mission completion in a disaster situation, and also the maneuverability to control its direction is required, and also the autonomous takeoff for a repeated mode switch from terrestrial to aerial mode is required, because once you land, we might want to fly again, and in that case, we really have to take off again, so we need that ability. And we can find a good example from nature. The birds can walk, run, hop, and can take off by using hopping, and also they can fly. So we're inspired by the birds, and we want to build a robot just like a bird. And at this moment, we're especially interested in the leg, which provides the speed, maneuverability, and autonomous takeoff. And also, it's very light, that it only takes 15% of the entire body weight. So our first objective is to find a lightweight leg design that can provide walking, running, and hopping. The lightweight is quite important because this is flying. We're going to build a flying machine, and the weight is quite critical. So we look at designs which have single actuator per leg in order to reduce the weight. And these robots used elastic actuation to overcome the limited power output from the actuator by using elastic elements for storing energy. So the working principle is to use the actuator for storing energy in the elastic element and release the stored energy quickly to have explosive locomotion. So it could increase the peak power output. And the orange box robots are using parallel elastic actuation, and the green box robot is using series elastic actuation, and which is called PEA and of SEA. And you can see that mostly PEA is used for the robot, and that's because PEA can store higher elastic energy compared to SEA. And I'm going to explain in more detail about this mechanism in the next slide. So you can see the diagram here. So the left one is the PEA, and the right one is SEA. So the PEA connects the actuator and the elastic element in parallel. So the energy status and the foot trajectory are coupled. And the elastic element releases energy when a trigger is activated, and the connection between the actuator and the leg is broken. So PEA can store the elastic energy as much as it wants with high gear reduction ratio. And by slowly storing energy, you can reduce the required motor torque. And also by releasing the energy late, you can store more energy and release more energy. But the connection break does not allow PEA to generate a cyclic foot trajectory, which is required for walking. Walking really needs a cyclic foot trajectory, but then it cannot, because it only can generate a catapult-like motion. It's storing energy and shooting the leg, just like catapult. That's what PEA is. And on the other hand, the SEA connects the actuator and the elastic element in series. So the energy is stored with external force. So because the actuator and the leg is connected to each other all the time, So SCA can actually generate the cyclic trajectory for walking as long as the actuator motion is not limited. However, the energy charge and release is totally passive, so we cannot really control the energy release timing and the amount of energy, which leads to limited elastic energy. Actually, the example I brought up here, the salto, this one is based on SCA. But then, although SCA should be able to generate cyclic trajectory, this mechanism tried to increase the amount of energy, and that requires some specific design in the linkage design of the leg, and actually that limited the motion range of the actuator. So actually, salto also could not have a cyclic trajectory, although it's a series elastic actuation. So I brought up a solution. So we introduced a custom elastic actuation called the inverted cam. We named this device as the inverted cam because we inverted the stationary and rotating parts from the conventional eccentric cam. And so this device has a radius reducing shell. So I'm not sure you can see this point on my mouse. So this is a shell which has reducing radius. So it has the largest radius here, and the radius continuously reducing. So you can see the video here. So as the output shaft rotates, connected to the actuator, you can see this angle here where the spring is embedded. This one is storing energy. So I'll show you again. So as I pass through this reducing cam-shaped shell, you can see the spring is saving energy. And at the exit here, you can see that the energy is released at once. So I'm gonna, yeah. So in more detail, the inverted cam is actually based on a series elastic actuation, but it stores energy using a parallel structure with the shell. So this is where we store the energy, and shown in the right. So while we're charging the energy, we connect the series elastic actuation with this inverted cam in parallel. So you can see it you're doing so by having this contact here. So you can see that the shell is having contact with this linkage here. But then when it leaves this shell, then we release energy, and the connection between the inverted cam and the leg is not broken. So it only acts just like a series elastic actuation. So this is how we could combine the series elastic for the entire system, but then we charge the energy by using the parallel elastic actuation. So this was my solution to solve the problem. And to design the inverted cam, we would like to have a model telling us how much torque will be required to run the system. And so we can select the motor and optimize the required torque profile. So we analyze the inverted cam with the virtual work principle to calculate the required torque to run the system. So just these equations, so let me first explain with this. So the L1 is this link, the link connected to the output shaft, and L2 is the other link which is connected to there is a torsion spring embedded here, and this is the L2 is from the torsion spring to the wall here, and we call this length from the output shaft to this contact point as R. And the virtual work principle tells that the work from the motor should be equal to the work in the work done to the spring, assuming ideal condition where we don't have friction loss or anything. So the work is simply the torque time, the change in the data at the angle, and also for spring is also tau, the torque from the spring times the change in the data. And assuming we have a constant spring constant, which is Ks, or we can rewrite the torque of spring as K times data S, the angle of the spring here. And so it tells us that actually the torque of the motor is related to the relationship between the change of spring angle and the motor angle. And by using trig, we can calculate the spring angle, the relationship between the spring angle and the motor angle, where the equation showing up here. And actually the R here, which is this, is actually the function of data O, which is just data motor divided by the gear reduction we have So which is the gear is connected between this output shaft and the motor. So this we can say that R is a function of data M also. So and this data function R is actually a choice of the designer. So we can choose any function for this, which will change the torque of the motor. And just to give an example, I chose a linear function, this function, which is just simply telling that it has the longest radius length here. And now we're going to have linearly decreasing radius. And that's just this equation telling us. So I use this radius function, and I did some simulation and also experiments. So using that radius function I just explained, I did some experiment where this plot shows the experimental data. The mean value is marked with the solid, the black line, and the gray area tell us about the standard deviation. And the purple dashed line is theoretical calculation. And as you can see that we expect it to have an exponentially decreasing torque value for the motor. And we can observe that from the experiment actually. So it's decreasing with some noise there. So the energy efficiency was 43%, 0.9%. And we're expecting that the first of loss was the friction in the gearbox and friction in the linkage joint and also the motor joule heating. And the first of noise here, probably from the 3D printed gear, we use the 3D ABS material 3D printed gear. And there's inconsistent in the gear meshing, and also there's a rough surface of the shell, which is also 3D printed, so that can cause the noise here. And with this inverted cam design, now it's time to connect it to the leg. So here's the design for the linkage leg I designed. And the left one shows a plot how the linkage looks like and also the corresponding foot trajectory we have. So this stand phase one tells us when the cam is just storing energy, but still the robot is on the ground. And stand phase two is when the spring is activated to push up the ground. And swing phase is when the robot is in the air and trying to retract the leg back to the original position. And we use the Stephenson tree linkage, which is a 6-bar linkage. And we found this design with simulation and physical prototype iteration. We built and we tested the simulation and could find this design. And this one shows the actual CAD model and actual physical robot with indicating how this each the actual physical part correspond to this theoretical link design. So how did it actually work? So since we wanted to test the inverted cam with a single leg first, the only performance we could test was hopping. So this figure shows the full cycle with the status of the elastic energy level here and the cam and the robot status. So let's begin from here. So at the beginning with the descent phase in this cycle, we still have the energy store from which we stored already from the swing phase, and you can see it's bent here, and the robot just landed on the ground. And as this linkage moves around, so we store more energy, and the robot also moved the central mass a little bit, and we're about to leave the inverted cam here, and you can see the energy level is full, and it's kicking the ground now. And now we release the energy. We used some of the energy in this spring, and the robot is still kicking the ground up. And finally, when the energy is all used up and the robot is now in the air, and we entered the swing phase. And in the air, it still because the inverted cam can provide cyclic trajectory, we are moving this link to store energy while we are in the air. And we are now back again, we arrive to this status where we are ready for the next hop. And so we need a model to simulate the behavior of the platform equipped with the inverted cam. So we can tune the design to improve the performance. And so that's why I had to have a model. And we used generalized coordinate to model the system. So the Q1, Q2, and Q3 is for the central mass of the body, the main body. So this is virtual DOF where, and this Q1 is for the horizontal displacement in X direction, and Q2 is for a vertical displacement in Y direction, and Q3 is the angle of the pitch angle of the body. We're only talking about 2D, so there are only 3D DOF for this. And to there, we have Q4 and Q5, which corresponds to the lag angle with respect to the body frame. And Q5 is the length of the lag. So we use these generalized coordinates to express the robot. And here is the classic equation of motion. And to have this model, we had to put the foot constraint here because the robot is having contact with, the robot is having contact with the ground, we assume that the foot is working as a pin joint. So that's why we had to put the constraint on the foot. And also there are some external forces where, because this one is one-leg robot, we need some support to prevent it from tilting over like back or forward. So we put some claw to prevent and to make it balance when it's not moving. So that's the F external. So we gave the foot constraint like this. So we know the foot position, calculating from the space frame. And we assume that the velocity at this point, PF is dot PF is equal to 0. And also the acceleration at this point should be equal to 0. So by using a relationship, we could get the required constraint reaction force at this point, and we could have a model with the foot constraint. And actually the robot does not really have the Q4 and Q5. They are kind of imaginary values. The way actually it works is that using the 6-bar linkage, the robot is generating some foot trajectory. So we have to convert that motion, the linkage motion, to the Q4 and Q5. So first we have to convert from the inverted cam joint motion to foot trajectory using the kinematics and dynamics. From there, we had to consider the spring activation when the crank leaves the shell. And the foot trajectory was converted to Q4 and Q5 using geometry, as you can see here. From here, where our central mass is here, we can calculate using geometry where the Q4 and Q5 will be for each point. So we can know what Q4 and Q5 is. And from here, because we know the acceleration of this trajectory, we can also get the acceleration required for Q4 and Q5. So we can use that value for the input for Q4 and Q5 in the dynamics. So with the model I have, we simulated the performance in terms of trajectory, velocity, and pitch angle. And you can see here that the blue dashed line is without the spring activation, and the red line is with spring activation, and this dashed line in orange is the swing phase. So we observed that the distance traveled was 26.3 centimeter, and the height gain was from this point to here, the maximum height was 12.4 centimeter. And if you look at the velocity, and this dashed line just indicates when the spring is activated and when the robot entered the swing phase. So we found out that the peak X velocity was 0.75 meters per second, and the peak Y velocity was 0.86 meters per second. And we also observed the pitch angle while whether it's going to be balanced or not. So we can see that at the beginning, the pitch angle was increasing, but then it tried to come back to 0, as we can see here. So yeah, and with this model, we actually built the robot and tested. Here's the result. So the setup was using the motion capture at 60 Hertz with OptiTrack. And we connected the robot to a boom system because it only has single leg, so it's hard to balance. So with just a single leg. And we powered by a power supplier, although it can be powered with battery, just because I was doing the experiment repeatedly, and then I didn't want to swap the battery each time So, but still I carry the battery here, so I don't have any advantage for like reducing the battery. So the battery is still here. So let's see the performance. The video speed is in 1.8. So this is how it hops using the spring activation. And you can see that it safely landed on the ground without falling over. So yeah, when we compare this to the this experimental data to the simulation, so this gray and the black line here shows the mean value over 10 trials and also the standard deviation. So you can see that the distance traveled was 21.31 centimeter, and that was actually 19% error. But in height, it could gain 11.3 centimeter, but that was 8.9% error. And if you look at the velocity plot, I thought which is more interesting, where the gray and black here is for x velocity for experimental, and this red line with the pink area is the y velocity experimental data. And this dashed blue line is for y velocity simulation, and this light green is for x velocity in simulation. So if we look at the y velocity first, you can kind of see that the trend is quite similar, where it draws a curve and sudden increase in velocity when the springs activated and falling down here. So, and also the x velocity, we can see that it's increasing, and then it should be stayed at the same velocity. But somehow, I think when the robot is hopping, there was I think the claw was making some sudden contact with the ground, which was actually dropping the velocity suddenly here when it tried to leave the ground. So that's why. But yeah, so generally the trend was quite matched well. And for the pitch, although this increasing the pitch angle was happened later, but we could observe that this one can actually stabilize itself when it tries to land. And I think this sudden jump here is also caused from the moment when it tries to leap. The foot was having some weird contact with the ground. I think that's why it happened. And for the velocity, the percentage error was 22.7 in x velocity, and there was 5.8% error in y velocity for the peak velocities. So there are some huge error for x distance and x velocity. I'm assuming that first for the error is coming from the boom connected to the robot. Actually, it has to carry if you look at, again, the robot is connected to the boom, and it has to carry the weight there like that. And although we've installed some bearings in there, it's not perfect. So it cannot really provide ideal condition. So I think that's why it loses some velocity in extraction. Yeah, and the air resistance also quite wide place and role there. So conclusions to summarize, so the inverted cam is elastic actuation system providing cyclic trajectory and have controlled energy charge and release. And the profile of the inverted cam shell radius determines the required input torque, and we can tune that by choosing a proper function of the radius. And the inverted cam was installed and tested on hopping platform. And the hopping platform was able to hop and stably land. And the experimental and simulation results were matching quite well. And that's it for my presentation. And thank you for listening to my presentation. If you have any question, please let me know.